Pressure. In everyday life, the term pressure is a common utterance, of course used in various contexts, both scientific and in ordinary talks. But the scientific meaning of pressure goes beyond what many people think, and just as often as the word itself is used, so is the application of the concept of pressure in everyday life. So what is pressure? Imagine dropping an apple against the sharp edge of a knife. Then try with the blunt side. What do you think? Now imagine this balloon and a nail. If you press the balloon against the nail, it will burst. What if we had a huge number of nails, say 100, and press the balloon against them? You see, it takes a larger effort to burst the balloon with many nails. Now, two things are common in these two scenarios. First, there is a force applied on one object against another. And secondly, there is an area of contact between the two objects. The impact of the applied force is larger when the force acts on a small area than when the same force acts on a larger area. By definition, pressure is the force acting normally or perpendicularly per unit surface area. Mathematically, pressure is equal to force over area. The units of force is newtons. Units of area is meter squared. So the units of pressure is newtons per meter squared. This is also called Pascal, named after Blaise Pascal, whom we shall meet later on in the chapter. 1 Newton per meter squared is equal to 1 Pascal. Other units used include millimeters of mercury and atmospheres. From that mathematical expression, it is obvious that for a small area, pressure is high and vice versa. For example, if a man weighing 75 kilograms is standing and the area of his feet in contact with the ground is 1.5 meters squared, what pressure does he exert on the ground beneath? So, pressure is force over area, and the force is equal to the weight of this man. So we convert 75 kilograms into newtons by multiplying with 10. So we get 750 newtons. Force over area over 1.5 gives us 500 pascal. Suppose he now stands on 1 foot. How much pressure does he exert? Notice that by standing on 1 foot, the area in contact with the ground is reduced by half. That is a half of 1.5, which is 0.75 meters squared. However, his weight doesn't change. So new pressure is 750 over 0.75, which gives us 1000 newtons per meter squared. The pressure doubles when the area is halved. So the man will experience fatigue faster when standing on 1 foot. It is therefore not surprising that trucks carrying heavy loads usually have many tires as compared to light and small cars. This increases the total area in contact with the road. By distributing the weight or the force over a large area, pressure is tremendously reduced. Otherwise, few tires would burst due to the high pressure exerted on them. At this point, it is important to mention that anything that has weight exerts pressure on another object. Even the atmosphere, comprising of all the gases, exerts pressure on objects on the Earth's surface. And this is called atmospheric pressure, and it is due to the weight of the air column surrounding the Earth's surface. We'll come to that later, but let's first look at pressure in liquids. Now imagine you have this bottle and you make holes at varying depths along it, such that water gushes out. You notice that the water shoots the longest distance from the lowest hole. And the reason for this is that the water at this level experiences the highest pressure. As you go down, the weight of water over each of the holes increases. This therefore increases pressure as depth increases. Now, on your screen is a series of interconnected tubes of different shapes. If we pour a liquid in one of the tubes, we observe that the liquid stands at the same horizontal level in each tube, even though the area of cross-section of each tube is different. This is because the pressure at the top of each tube is equal to the atmospheric pressure. The pressure at the bottom of each tube will also be equal. This shows that liquids seek their own level. Let's change that into a U-tube and again see the liquid levels. Now when water is poured into a U-tube, it will flow into the other arm. The water will settle in the tube with the levels on both arms being the same. But when one arm of the U-tube is blown into with the mouth, the level moves downwards, while on the other arm it rises. This is caused by the pressure difference between the two arms. The pressure increases on the arm that is blown into and causes water to rise on the other arm. So exactly what factors affect the pressure in liquids? Let's perform several experiments to help us draw conclusions. We take a thin sheet of rubber from a balloon and stretch it over the mouth of a thistle funnel with a short stem. We connect the thistle funnel via a rubber tube to a U-tube mounted on a vertical board with a graduated scale. We then fill the U-tube with a colored liquid. You see, the level of the liquid in the U-tube is the same. We fill a cylinder with water, then we lower the thistle funnel to a depth P in the cylinder. We know the difference in the levels of liquid in the U-tube. This difference is equal to the pressure exerted by water at depth P in the cylinder. Next, we lower the thistle funnel to a depth Q. Again, we note the difference in the level of the liquid in the U-tube, which is equal to the pressure exerted on the thistle funnel at depth Q. So you notice that the pressure exerted at depth Q is larger than at P, shown by the larger difference in the liquid in the U-tube. Therefore, the pressure at a point in any liquid increases with depth from the surface of the liquid. Again, observe the differences in the levels of the liquids in the U-tube when the thistle funnel is dipped in water, glycerin, and alcohol. You notice that the difference is larger when the thistle funnel is dipped in glycerin and least in alcohol. This is because glycerin has the highest density of all the liquids and alcohol has the least. Conclusively, pressure at any point inside a liquid increases with increase in density of the liquid. Lastly, we record the difference in the levels of the liquid columns with the thistle funnel pointing vertically downwards, then vertically upwards, and towards the sides of the tall cylinder for the same depth. you realize there is no change in the level of the liquid column. Therefore, pressure is the same in all directions about a given point within the liquid. So with these experiments, we can conclude that 1. Pressure in a liquid increases with increasing depth from the surface of the liquid. 2. Pressure in a liquid increases with increasing density. And 3. Pressure in any liquid at a particular depth is the same in all directions. So for a swimmer at a point A and B, pressure exerted by water on him or her is equal, irrespective of the fact that the water volume around A appears larger. Only the depth affects pressure, not volume. So how do we calculate pressure in liquids? Now carefully consider a liquid in a container on your screen. If A is the cross-section area of the column, height the height of the column, and rho the density of the liquid, then volume of the liquid is equal to cross-section area times height, that is A times H. Mass of the liquid is given by volume of the liquid times density. That is from the fact that density is mass over volume. So mass of a liquid is A times H times rho. Therefore, the weight of the liquid is equal to mass of the liquid times the gravitational force per unit mass, which is represented by G. So the weight of the liquid is given by AH rho times G. Definition of pressure. Pressure is equal to force over area. Force is the weight of the liquid, so AH rho G over A. The A cancels out and pressure is equal to H rho G. Therefore, pressure exerted by the column on A is given by H rho G. From the formula, it can be concluded that pressure due to a liquid column is directly proportional to height of the column and the density of the liquid, and it does not depend on the cross-section area of the container which holds the liquid. The formula is also used to determine pressure due to gas columns. A MAPO is lying at the bottom of an ethanol tank 2.5 meters deep. What pressure is exerted on the marble given that the density of ethanol is 0.8 grams per centimeter cube? We are given there to take G to be 10 newtons per kilogram. Now we first convert that density, grams per centimeter cube, into kilograms per meter cube. And how we do that is by multiplying by 1,000. If we do that, we get 800 kilograms per meter cube. Pressure is H rho G, so we have 2.5 meters times 800 kilograms per meter cube times 10. So we get 20,000 Pascal. Transmission of pressure in liquids. Now here I got a tube with a piston at one end and a round bulb at the other. You notice the holes are made on the bulb in all directions. We fill the tube with water and push the piston and observe how water spurts out. Any difference? No. You will observe that water comes out of the holes with equal pressure. It therefore means that the pressure I apply by pushing the piston is transmitted equally in all directions. We can also demonstrate that here. We observe that the liquids stand at the same horizontal level in each tube. This is because the pressure at the top of each tube is equal to the atmospheric pressure. If we apply a force on the syringe, it exerts pressure on the liquid, transmitted equally through the liquid. And you can tell that because the liquid rises to the same level in all the capillaries. Again, if you look at these two vertical cylinders with pistons and connected via a horizontal pipe, if I push down one of the pistons, the other is pushed up. What is happening is that when I apply a force on one of the pistons, it exerts pressure in the liquid. This pressure is transmitted through the liquid to the other side. There, it creates a lifting force on the other piston, pushing it upwards. So then, how much force will be exerted on the other piston? One advantage of liquids, unlike gases, is that they are not compressible. And that is why the pressure exerted at one point is transmitted equally and unchanged. You see, both A and B are equal. So let's say they have a cross-section area of 2 meters squared. If we apply the downward force of say 50 newtons on A, how much shall we get at B? Pressure exerted on the liquid is given by force over area, that is 50 over 2, which gives us 25 newton per meter squared. This pressure is transmitted equally and unchanged up to piston B. How much force will it generate? Pressure is given by force over area, and therefore force is equal to area times pressure. Area of B is 2 square meters. We multiply that by pressure, 25 newtons per meter squared, and we get 50 newtons. The same force is generated at B. Pressure applied at one point in an enclosed liquid is transmitted equally to all other parts of the liquid. This is called Pascal principle, named after Blaise Pascal, who first explained it. Gases would also transmit pressure in a similar way, but they are compressible. What if the area of the pistons varied? How would that affect force? One way to find this out is to use a simple system of 2 syringes, tubing, and water. When we apply force on one of the syringes, the other goes up. Because the fluid is incompressible, the pressure is transmitted from the first syringe to the other, causing it to fill with water. You will notice that it is easier to push the smaller syringe down than the larger one. The pressure is equal in all parts of the fluid, but when the area of cross-section has increased, the force must also increase proportionally for pressure to remain the same, since pressure is force over area. This results in multiplication of force, a concept applied in hydraulic lifts. Applications of the Pascal principle, and we start with that hydraulic lift. In a hydraulic lift, there are 2 cylindrical tubes, A and B, of an equal area of cross-section fitted with valves V1 and V2. These cylindrical tubes are connected at the bottom by means of a horizontal tube. These cylinders contain pistons P1 and P2, which can slide up and down within the cylinder. Observe that the area of cross-section of B is larger than that of A. The tubes are filled with water in such a way that the levels of water in both tubes are equal. The smaller cylinder is called the pump plunger and the larger one is called the press plunger. To press down or raise the pump plunger, there is a lever arrangement with a handle. When force is applied to piston 1, it exerts pressure on the liquid contained in the smaller cylinder or the pump plunger. According to Pascal principle, this pressure is transmitted to the piston of the press plunger, and due to which piston 2 is pushed upwards. Since the cross-section area of the pump plunger is less than that of the press plunger, the applied force is multiplied. Hence, by applying a small force on the small cylinder, we can lift a large weight kept on the piston of the larger cylinder. For instance, if the pump plunger has an area of 2 meters squared and the press plunger has an area of 20 meters squared, we apply a force of 120 newtons on the pump plunger. Pressure produced is given by force over area, which is 120 over 2, giving us 60 newtons. This pressure is produced at the small cylinder. It is transmitted to the press plunger unchanged. How much force will it generate there? Force is given by pressure times area, 60 times 20. 20 is the area of the larger cylinder. It gives us a force of 1,200 newtons. So a force of 120 is multiplied 10 times to give us 1,200 newtons. This force multiplication allows for massive weights to be lifted with application of a small force. The next application of Pascal principle is the hydraulic brakes. What slows down a speeding vehicle is the application of brakes. It applies the Pascal principle where a force applied on the pedal creates pressure in a liquid, which is transmitted to pistons over long distances without pressure loss. Diagrammatically, it consists of a brake pedal, a master cylinder, a wheel cylinder, and we have a brake shoe. So when the pedal is pressed, it pressurizes the brake fluid in the master cylinder. This pressure is then transmitted to the wheel cylinder. There, the pressure energizes the brake piston. They move and pressurize the brake shoe, making them to move. So this is the complete system for all the 4 wheels of a car. Important to note is that the wheel cylinder is larger than the master cylinder. So force is multiplied. So when brakes are applied, the foot pedal is pushed, due to which pressure is exerted on the fluid in the master cylinder. This pressure is transmitted equally and undiminished throughout the fluid and into the piston of the wheel cylinder. Therefore, the pistons get pushed outwards and the brake shoe gets pressed against the rim of the wheel, due to which motion is diminished. On releasing pressure on the pedal, the return spring forces the fluid out of the wheel cylinder back into the master cylinder. So the next time you see this big truck slow down, you will imagine what goes on inside, won't you?
Next, atmospheric pressure. Now, the atmosphere surrounding us is a deep ocean of air extending for kilometers above us. So we live at the bottom of an ocean of air. Gravity pulls this mass of gas, creating pressure. The pressure is greatest at the bottom. If you have a small table 1 meter squared, the force on that area created by air pressure is approximately 101,000 newtons, equivalent to the weight of 10 cars sitting on that table. If air pressure can generate such huge forces, why don't we notice it? How comes the table doesn't collapse? Indeed, pressure in a fluid like air transmits in all directions, not just downwards. This means that the 101,000 newtons of force pushing down on the tabletop is balanced by an equivalent force pushing up. The forces balance. Equally, our bodies are not crushed because the fluids contained in our bodies exert a pressure that balances the atmospheric pressure. This demonstration reveals the presence of atmospheric pressure. Fill a glass with water. Take a piece of card large enough to cover the top of the glass. Lay the card on the glass, hold it in place, and turn the glass upside down. You notice the water stays in the glass. This is why. The card provides a rigid membrane between the water and air in the room. Air pressure pushes up the card. Air pressure is not pushing down on the water because there is a vacuum at the top. It pushes on the outside of the glass, but this does not affect the water inside. The only downward force on the water is its weight, which is easily supported by the upward air pressure. If you drill a hole at the top of the glass, air pressure will push the water down and the water will spill out. Atmospheric pressure is so important we couldn't live without it. The body uses atmospheric pressure to move air in and out of our lungs. The diaphragm, a muscular membrane below the lungs, alternately contracts and relaxes, changing the volume of the chest cavity, which changes the internal pressure. Low pressure allows air at atmospheric pressure to move down the trachea and into the lungs. High pressure forces it out. Without atmospheric pressure, we couldn't breathe. Atmospheric pressure also plays a role in the function of many devices, including water pumps, syringes, and drinking straws. When you use a drinking straw, you are not sucking the liquid up the tube. Air pressure pushes the liquid up the tube.
Now imagine if you took a can and hit it in a Bunsen flame and then suddenly dip it in cold water. Watch what happens. The can collapses. Now heating drives most of the air out of the can. The steam inside expands and balances the atmospheric pressure outside. However, on cooling, the steam condenses, lowering the pressure inside the can. The can therefore collapses in a bid to re-establish the balance. Let's see the maximum that can be supported by atmospheric pressure. Now, if we have a long glass tube of about say 100 centimeters, closed at one end and open on the other, this tube is filled completely with mercury. It is inverted into a pool of mercury. Now, an empty space is created by the tube on the top side. The mercury column in this glass exerts a downward pressure. For the height of this column to remain constant, there must be a counter pressure to hold it up. This is the atmospheric pressure. The height of the mercury in the tube is measured from the reservoir surface, and the length of this mercury column is equal to the pressure exerted by air. Under normal conditions, the pressure is around 76 centimeters or 760 millimeters of mercury at sea level. However, pressure is generally lower at higher altitudes. So then, how do we measure pressure? Now, the first instrument used to measure pressure is a U-tube manometer. A manometer is an instrument that can be used to measure fluid pressure. It consists of a U-tube filled with water or any other suitable liquid like mercury. Suppose one limb of the manometer is connected to a gas supply. Now, due to the pressure of the gas, we give it Pg, the level of water in the other limb rises, say to Y. The difference in water levels is the difference between the gas pressure, Pg, and the atmospheric pressure, Pa. Since X and Z are at the same horizontal level, pressure at X equals to that at Z. Pressure at X is the pressure of the gas, Pg. Pressure at Z is equal to atmospheric pressure plus the pressure due to the column of the liquid. Therefore, Pg is equal to Pa plus H rho G. Since the density of the liquid and G are known, we can be able to determine the pressure of the gas if the atmospheric pressure is known. The next instrument is barometer. It has been shown that atmospheric pressure supports a liquid column in a tube. When this arrangement is used to measure pressure, it is called a barometer. At sea level, the column of mercury and water supported by atmospheric pressure is approximately 760 millimeters of mercury and 10 meters respectively. Mercury, which is slightly over 13 times denser than water, is chosen for atmospheric pressure measurement since it gives a much shorter and measurable column, because you won't want a column that is 10 meters high. The height of the column is the measure of the atmospheric pressure. At sea level, H for mercury is usually 760 millimeters. Now, since the density of mercury is 13,600 kilograms per meter cube, atmospheric pressure Pa is equal to H rho G. So we have 0.76 meters, that is 760 millimeters, times density 13,600 times 10 G, which gives us 103,360 Newton per meter squared or pascals. This is the standard atmospheric pressure, and it's sometimes referred to as atmosphere. Another instrument for measuring pressure is a floating barometer. Usually, the simple mercury barometer cannot be used for accurate measurements of atmospheric pressure. An improved version called the floating barometer is used where high precision is required. It consists of a mercury reservoir. The mercury level can be adjusted by a screw provided underneath. A brass tip is fixed above the mercury level, which coincides with the zero of the scale of the barometer. A narrow glass tube filled with mercury is inverted and inserted in the mercury reservoir. Adjusting the screw, the mercury level can be made to coincide with the tip. The reading of the mercury level M in the tube gives the atmospheric pressure. A vernier scale is also provided for accurate measurement of the reading. We can measure atmospheric pressure accurately with a Fortin's barometer, but it cannot be shifted from place to place, so it's usually used as a standard barometer. Then we have pressure gauges. Now, pressure gauges are portable and are used mostly for measuring gas pressure, tire pressure, pressure of compressed air in compressors and steam pressures. They are basically made of coiled flexible metal tubes which uncoil when the pressure inside decreases. The movement of the tube is made to drive a pointer across a scale through a combined system of levers and gears. Next, we look at some applications of pressure in gases and liquids. When we start with the bicycle pump. Now, this is a simple form of compression pump that doesn't use electricity. There are several components. First is the body of the pump, which is the outside of the pump. The compression chamber stores air inside the pump. A hose is attached to the compression chamber and is attached ultimately to the tire valve. Inside the pump body is a piston which moves up and down, compressing air in the compression chamber and forcing it through the hose to the tire. It is connected to a handle which the user holds. Finally, there are two one-way valves. The inlet valve allows air to flow into the chamber and never out. And the outlet valve allows the air to flow into the tire. Both valves work in conjunction with the piston. The piston rises when the handle is pulled. This draws air inside the body of the pump. Air then enters the compression chamber. The inlet valve opens to allow this. The piston is then lowered. The inlet valve closes. Due to high pressure in the chamber, the outlet valve opens and air flows to the hose and to the tire. Lastly, we look at the siphon. A tube, mostly plastic or rubber, can be used to empty tanks or draw petrol from petrol tanks in cars. When used in this way, it is referred to as a siphon. The pressure at the surface of the liquid is atmospheric. Since the end C of the tube is below the surface A by height h, pressure at C is greater than that at the surface. The tube is first filled with the liquid. After this, the liquid will continue to run out so long as the end C is below the liquid surface.
The Royal Institution in England had very quickly, in the early 1800s, devised a very large bank of batteries. In fact, the batteries consisted of 2,000 cells. If these cells produced each about 0.7 of a volt, you can imagine even 2,000 of those connected in series would have given quite a large amount of electric current. Michael Faraday started experimenting with this new form of energy. And it wasn't long, as one can imagine, before all sorts of discoveries were made. Ørsted realized very quickly that if an electric current was passed through a wire, that a magnetic field could be generated. Michael Faraday realized that if you took one piece of wire and you laid it parallel with another, passing current through one of the wires induced, by not physical connection but by electromagnetic connection, induced a voltage in the wire lying parallel to the first one.